So we're moving on to our third concept for linear algebra, eigenspace. So here on the board we have a little warm-up. We have a matrix A and we need to solve for the complex diagonalization of this matrix. And so we'll discuss more about what diagonalization is, but right now let's go through this warm-up. So the first thing we need to do is we need to find the eigenvalues of A. So we're going to subtract by lambda, so we're going to need negative lambda, negative 2, and 2. Okay, so then the characteristic equation is lambda squared minus negative 4 is equal to 0, so plus or minus 2i. If we recall correctly, c is equal to a, negative b, b, a, and then a is 0 and b is 2 here, so that's going to be the same thing that we had already. We need to solve for p. How are we going to do this? Well, remember p is equal to the real part of the vector and the imaginary part of the vector. So we just need to solve for the vector. Alright? Now let's do that. So, how are we going to... So, how are we going to do that? Well, we know that the eigenvalues are 2i and negative 2i. So let's subtract by one of them. Let's subtract by negative 2i. So now we have negative 2i, but it's minus, so it's plus. So now we have 2i, negative 2, 2. Alright, we can divide everything by 2. We get 2. We can divide everything by 2, so we get 1, negative 1, but this is I, 1, and then I, right? And then augment with 0, because we know that it's going to be 0. Next thing we're going to do is we're going to multiply the top row by I. So we're going to get I squared, which is negative 1 times I, which is negative I, 1 and I, 0. And 0, and then we'll just add the top row and bottom row, and so we get 1 I 0 0 0 0. All right, now we've solved for one row, right? This is what we got there. So we got 1 I this. So that means that V is equal to, because we know that this means that V1 is equal to negative I times V2. Okay, so we get 0, 1, negative 1, and 0. Alright, so that means that our V is that. So we know that P1 is equal to, so actually that's just the entire P, because it's the real part and the imaginary part. So we know that P is equal to 0, 1, and then negative 1, 0. And then C is equal to 0, negative 2, 2, 0, and then we're done. So our first essential question is, what are our eigenvalues and how are they determined? Well, an eigenvalue, as I expressed in that last video, is where you just have A times some vector x, and if x happens to exist within the eigenspace, or the space in which that eigenvalue lies, then you're going to end up with a dilation of that vector, either a stretch or a shrink. Now, if it's a complex eigenvalue, which actually relates to essential question number 4, so now I don't need to go over that one, which is a rotation, right? And I actually went over that in the last video, and so that's the explanation of the difference between there, and I already solved a diagonalization of a complex one, so we don't need to do that again. So the question is, how are the eigenvalues determined? Well, like I said, you do the same thing like you did with the Markov chain. Remember, a Markov chain, right? The steady state vector had an eigenvalue of 1. And as you recall from there, what we did was we said, well, AQ is equal to the identity matrix with the same dimensions of A times Q. So AQ minus IQ is equal to 0. And so A minus IQ is equal to 0. Right? And so if we know that the eigenvalue is 1, well then this is just a minus 1 times I, right? Q equals 0. And so now if we replace 1 with just the general eigenvalue, lambda, then we get a minus lambda I, and then x instead of q is equal to 0. This is the part that is important, that a minus lambda I. And then you just solve for you just know that the determinant of a minus lambda I is equal to 0. So if I have a equal to 1, 0, 0, 1, then I know that a minus lambda I is going to be equal to 1 minus lambda, 0, 0. And then I solve for the determinant, so we know the determinant of a minus lambda I is equal to 1 minus lambda squared minus 0, right? We know that's equal to 0. So we know 1 minus lambda is equal to 0, and so lambda is equal to 1 with a multiplicity of 2. Right? And so then that's how you solve for the eigenvalues of a matrix. So we've already done essential question number 2 with that one essential question. So the third essential question is, what does it mean to have an eigenvalue of 0? An eigenvalue of 0 means that the matrix A is invertible. The next question that we haven't already done is, what is an eigenbasis and how is it determined? Well, an eigenbasis is just the basis for the eigenspace, which is just the subspace for the subspace of the matrix that refers to a certain eigenvalue of said matrix. One thing you need to know is that for triangular matrices, the eigenvalues are the values on the main diagonal. 1, 2. So first we know the eigenvalues are going to be 1 and 2. In order to find the eigenbasis, what we do is we find the null space of a minus lambda I. And that is actually related to our next question, which is, how do eigenvalues relate to the null space? The answer is that finding the null space of a minus lambda I, the basis for the null space, right? When you find a basis for the null space, this is the same thing as the eigenbasis. The next essential question that we haven't already gone over is, how do I diagonalize a matrix? Now, we diagonalize a matrix by doing A is equal to P d P inverse for matrices with real eigenvalues, with only real eigenvalues. But for ones with both real and complex, or just complex, then we have to do PCP inverse. Then you need to have n distinct eigenvalues, which means the sum of the algebraic multiplicities has to be equal to n, and the sum of the geometric multiplicities also has to be equal to n. But the number of eigenvalues doesn't necessarily have to be n in order to have n distinct. But that's what you need in order to diagonalize a matrix. Now, P is just a matrix filled with just the eigenbasis. And then D is just a diagonal matrix that has the eigenvalues on it. And it's different for complex, where C is equal to A negative B, B, A. Alright? Where A plus or minus BI. Where the eigenvalues are equal to A plus or minus BI. The next question is, how can I determine if two matrices are similar? So, similar matrices are matrices that have that can be written in terms of a diagonalization of the other. Now, what does that mean? It means that if I have a matrix A like this and a matrix B like this, then I can rewrite this as B is equal to P, A, P inverse. Or P is the eigenbasis of the eigenvalues of B. This matrix is not diagonalizable, by the way, just in case you were wondering. It's not diagonalizable. Now, the reason why it's not diagonalizable is something that you have to find out for yourself. But because it's not diagonalizable, you can't rewrite, these matrices aren't similar even though they have the same eigenvalues. So just because they have the same eigenvalues does not mean that they're necessarily going to be similar. And so the last essential question is, how do I create a page rank? Well, a page rank is, we'll do a Google page rank represented by matrix G, right? Well, first thing we need to do is we need to find the page rank matrix for a certain ranking system. So if we have 1 here, 2 here, different nodes, right? And we have 4 here. Okay, so we have 6 nodes here. So what we'll do to set up the matrix is we have, right, 1 goes to 2, n goes to 3, and to 4. So what we do is we set up a square matrix, alright? And then we say that, well, this is 1, 2, 3, 4, 5, 6, and this is 1, 2, 3, 4, 5, 6, right? Also, that as well. We'll do that too. Okay. So, first thing we need to do is we need to go 1. Now, how many times does 1 go to 1? Well, 0. How many times is out of 0, right? Out of how many branches does it have? Well, it has 1, 2, 3 branches, right? And it goes, 1 is 0 of them. 2 is 1 of them, so that's 1/3. 3 is 1 of them, so that's 1/3, and 4 is 1 of them, so that's 1/3. The other ones are 0. Alright? Next step, 2 to 1. Does not go to 1, 0. How many passes does 2 have? 1. Alright. So then 2 to 2, 0, 2 to 3, 0, 2 to 4, 1. As you can see, the sum of the columns is 1. Next, how many branches does 4 have? 1. What's the probability? 3, sorry. 3. How many branches does 3 have? It has 2. And so, how many times does that go to 1? 0. Does it go to 2? 0. Does it go to 3? 0. How many times does it go to? And then how many times does it go from 3 to 4? Well, that's 1 out of 2. 5 is 0. And then 6 is 1 out of 2. Alright, next step, 4. 4, how many branches does it have? 1. Well, that's going to be 0. And it only goes to 5, so that's going to be 0, 0. And then that's going to be 1, 0. 5 has 2 branches, 1 to 3 and 1 to 4. So then we get 1/2 and 1/2. Last one is 6. 6 has no branches. Except the one coming to itself. Right? Because we can assume that if you're stuck at 6, you're just going to keep staying. You're just going to stay at 6. And so 6 is basically just going to 6. Right? But then the probability of that is actually not 100%. Because if you get stuck at 6, you're not just likely to go to 6. You're likely to go to any of the other sites. And so what we do is we actually separate this among all of the other nodes. So we get 1, 6 like this. Then, to create a Google PageRank with a damping factor of p equals 0.85, because there's a probability that you might go, you might have arrived from other node areas, right? Then, or go to other areas. Then what happens is that we have g is equal to that damping factor, 0.85, times the k matrix, which we do 1 minus the damping factor, so that's going to be 0.15, right? Then we just multiply that by the largest node, so that's going to be 1, 6, right? So we have just 0.15 times 1/6, so you get 0.15 over 6, and then we just do that times a 6 by 6 matrix with all ones in that matrix. And so then that's how you create a Google PageRank. The first true or false question says, if the columns of A If a square matrix A span R to the n, then A is diagonalizable. Well, remember how I gave that example 1, 1, like this, or this could be anything, right? The columns here span R squared, right? This is an invertible matrix, but it's not diagonalizable. The next question is the algebraic multiplicity of an eigenvalue can be 0. This is false. It can only be 1 or greater. Next one is if x is an eigenvector of A, then 2x is also an eigenvector of A. And this one is true because multiplying it by a scalar does not change its location in the space. It just gives it a dilation. It doesn't change its location in the space, which is the reason why ax equals lambda x, right? What it does is it's not changing its position in the space. It's just either rotating it, or it's either rotating the space with the vector, or it's just dilating, so it's either shrinking or stretching, right? Stretching or shrinking that vector and the space around, and not necessarily the space around it, but it still exists within that space. So this one is true. The question is the Google PageRank has a damping factor of 0.85. This is true. If A is 6 by 6 and has two distinct eigenvalues, both with a geometric multiplicity of 3, then A can be diagonalizable. Yes, this is true. A is diagonalizable because the sum of the geometric multiplicities is in fact 6. In order to have two eigenvalues, you need to have a geometric multiplicity of 3 for each and an algebraic multiplicity of 3 for each. Because remember, the sum of algebraic multiplicities is equal to n, and the sum of the geometric multiplicities is also equal to n. If A is n by n and n is odd, then A must have at least one real eigenvalue. This is true because note that complex eigenvalues come in pairs, come in conjugates, which you can recall from pre-calculus. Remember that pre-calculus section is on my website. And the thing is with that, in order to have 3 eigenvalues, so you know that you have 2 complex, and it's, say you have a 3 by 3, right? If you have one complex eigenvalue, then you know you have another complex eigenvalue because they always come in pairs of 2. And remember that the sum of algebraic multiplicities has to be equal to n, and so that means it has to be equal to 3. But in order to increase the geometric multiplicity of one of those, I have to increase the algebraic multiplicity of the other. So I need to add another eigenvalue, and it can't be complex because then I'd have to add another one. So I have to add a real eigenvalue to that. So there you go. That is it for this concept video, and the next one will be orthogonality.